Central Time, and I am your host, Dr. Matthew Richardson, and this is another session of CosmoQuest Astro Office Hours. So, as normal, I'm going to go ahead and verify that I'm actually streaming, so just please bear with me while I do that. Opening up my Chrome browser. Going to go ahead and navigate to Twitch and see what it shows me. I think so far so good. I think I see it myself. Although Twitch is showing that it's not really showing what it typically shows.
Central Time.
Okay, I'm good. I'm live. However, I'm still waiting to be able to see comments. Just give me a moment. I'm going to refresh the page and see what happens. Okay, let's do this. It always does this every time I start up these streams. I typically have to quit the browser, reopen, and then it gives me the ability to be able to actually see chat. So let's see. That fixes the problem. Okay, good so far. Yes, success. Hi, Peter. Let's go ahead and pop out the chat. No calculus today. No calculus today. I promise. If I plan on doing calculus, I will warn you guys in advance. Let's quickly say hi to everyone who's here. Hey, Susie. Hey, Larry of the G Cloud. Hey, Michael T. Mayer. Hey, Peter. And hey, Uncle Bill Druin. Welcome to today's stream, guys. So I'm actually going to end up... Hey, Guido. I'm sorry I missed your name there. My apologies. So we're actually going to just pick up where we left off in my very last stream. And we were talking about determining the maximum kinetic energy of the electron that's generated in the muon decay particle interaction. Interesting that I say particle interaction because it's not really an interaction, right? It's just a particle and it decays into other things. So it's not really interacting with another particle to do this. But I discovered that there was some errors in what I was saying in my last stream. And a large part of that was due to the fact that my notes were really, really messy. I was able to get the right answer, but I kind of mixed some things up as I was explaining things in my last stream. And as usual, every time you tell me about dinner, that makes me think about lunch. But I'm happy that you guys are actually able to do stuff like that. Because this is supposed to be kind of like a laid back, relaxed, atmosphere. If you want, grab some popcorn or dinner, and we just sit here and talk about science. So, let's go ahead and do a more in-depth recap of where we were at in our last stream. So, and I've also prepared another problem because I'm pretty sure that I'm going to finish up this problem, and then I'm going to have time left. So, all right. So I'm going to go ahead and scroll down. And so for this particular problem that we were working on, which is calculating the maximum kinetic energy of the electron in the muon decay equation, we end up determining that we need to be able to use two different types of concepts in physics. Those concepts being conservation of energy and conservation of momentum. And so I actually want to start with making the first correction to what I was saying in my last stream. So this first equation I'm showing here, and hopefully the whole thing will show, let's kind of like minimize it a little bit. Make it so that everyone can, okay. Is that option not available for me right now? I seem to have lost the ability to zoom in and out using my trackpad. Okay, let's see what's going on here. So this is definitely a Mac thing. All right, system preferences. Scroll and let's just see what happens if I do this. The options available. Oh, there we go. All right, that's better. So my computer just had a moment of not obeying the options that I had chose. So here we go. I can now control that. All right, you guys can see everything. Perfect. So conservation of energy will tell us that the energy before this particle interaction, that is before the decay of the muon, must be equal to the energy of the particles that you get, that is their rest mass energies, as well as their kinetic energies that they obtain from the interaction. So what I'm actually showing here on the left-hand side is the fact that we're assuming that the muon is at rest when it decays. And so it only has its rest mass energy, which is basically its mass times the speed of light squared, which is Einstein's famous formula, E equals mc squared. And then after the decay, we end up generating an electron and two neutrinos, one regular muon neutrino and one anti-electron neutrino. I mean, antimatter electron neutrino. So and I hope I said this in my very last stream. Each term for those particles should be total energies. And so what I ended up noticing was that, well, one, what I actually put here for each particle were their kinetic energies. So I'm going to modify this to be accurate, to be the actual what it should be. And all I have to do now is just basically eliminate from each bracketed term the most right hand term, which is basically I'm subtracting away the rest mass energy of each particle. So let me go ahead and make that modification. So I'm going to scroll down to where that equation is, which is right here. And for each of those terms, I'm going to get rid of the minus m of mass of the particle times the speed of light squared. And that will correct the equation. Well, partially correct the equation, actually. There was another mistake I ended up making, which I'll get to in a second. But this mistake was due to the fact that I had made more calculations than I needed to make, actually. And I began to start talking about something called the Q value in my last stream, which is the reason why I made this particular mistake in the PDF you're seeing here. But this will end up correcting the equation, partially at least. There's one more correction I have to make. And of course, corrections that I make here I'll end up having to account for in statements that I make later on in the PDF document. And the very last thing that I have to correct, and I believe someone even probably hinted at this, was the fact that the rest mass energy term underneath the square root is not complete. And that is for each of those terms, like for example, with the m sub e times c squared, that quantity should be actually squared in itself to make it dimensionally correct. So I'm going to go ahead and make that modification as well. Make sure I'm keeping up with comments as well. So everyone is getting a chance to eat right now. I'm kind of jealous. Okay, let's do this actually. This is square root. All right, that corrects it. That goes here. That should be squared. And lastly, this last one, this should be squared. Okay, this is correct. And so, as far as units are concerned, on both the left and right hand side of the equation, the units should be units of energy. And the actual unit that you're dealing with will depend on the unit system you want to use. In this case, I'm going to use a unit system that's highly convenient. You'll see later on as I actually start to do some arithmetic and stuff like that. All right, so this is actually corrected. And I'm going to, of course, have to make corrections later on in the PDF document, given the changes I've made here. But there's one more thing that I stated but didn't actually physically put in my PDF document, and it was for the conservation of momentum. And the idea here, of course, just like the conservation of energy, whatever the momentum was before the interaction, we should get the same momentum after. And because we've assumed that the muon is at rest, that is, it has the velocity of 0, that means its momentum was 0 before the interaction, or its decay, which means that the momentums or momenta of all the particles that are generated due to the decay, they should also their momenta should sum to also be 0. And of course, it can be a very complicated problem, right? Because you can imagine having a muon just resting in space. It decays and it produces these 3 particles, and they can go in all types of directions. The only condition, though, is that their momentum or momenta have to all sum to be 0. And so, given that the objective of this problem is to determine the max kinetic energy of our electron that's generated, the only thing that's really important to us is the corresponding magnitude of its momentum. Note, I'm only concerned with the magnitude, not necessarily the direction in which the particle is actually traveling. And this is something that we can actually use to make the problem a whole lot easier to deal with. So yeah, as I was stating, I ended up stating that we made the connection between the max kinetic energy of the electron is intimately tied into its the magnitude of its momentum. And after a few arguments, I end up getting down to the point that the momentum of our electron will basically be equal to, in magnitude at the very least, the sum of the momentum of the 2 neutrinos that are generated in the interaction, and that its momentum vector will have to be in the opposite direction of the momentum vector that you'd get, the resultant momentum vector that you'd get from summing the individual momenta of the neutrinos. But the one thing I wanted to add here, so I'm quickly looking at the conversation here in chat. Nothing but diversions here, Matt. You guys know I'm easily straight off course at times. But no worries though. I'm actually liking the conversations that you guys are generating here. It's actually quite interesting. And I might jump in a minute. But let me go ahead and continue with this though. So the one thing I wanted to add to the conservation of momentum that I'm showing here is that the key thing that's important to me is that the magnitude of the electron's momentum must be equal to the magnitude of the sum of the momenta for the two neutrinos. And because we're only concerned with magnitudes, the most convenient coordinate system to work with for this particular scenario would be a coordinate system in which most of the motions only occur, well, all the motion is occurring within a single axis. And you can do a bit of math to be able to do this. And in my last stream, I was going to go ahead and work through that, but I figured that there was probably no need for it to do that. All right, so I've added another line here to demonstrate that this is the most important thing that we're concerned with. That the magnitude of the momentum of the electron is equal to the magnitude of the sum of the momenta that you generate from summing the individual momentums of the neutrinos. All right. And we can drop the negative sign because before, I wonder if I'm saying that correct. I'm not saying this exactly correct. Well, I'm not showing it exactly correct. I think this is a little bit more accurate. There we go. I think that's better if I put it like this. And so the condition in which you get the maximum kinetic energy for the electron is in the case in which the momentum vectors of each individual neutrino are in the same direction, and then of course the momentum vector for your electron is in the opposite direction. So it's anti-parallel to their directions. But of course, that might not be the case. But as far as solving this problem, that's what you should imagine in your head. At least when you're trying to work out the math for this. I don't want to keep saying too much because I don't want to confuse anyone. Because in my mind, I'm thinking about the fact that if you do it in 3 dimensions, I mean, this line that you're generating essentially can be in 3 dimensions, or it could be along a single axis. All right. So moving along to what I was stating next, which was back to conservation of energy. So I'll scroll down here. So I'm going to have to actually modify this too, because again, earlier I ended up making some changes, so I have to make the same changes that I made above. What's the best way to do this? Let's do this. So I'm going to comment out these lines because I see that they're making some, so we can see everything together. There we go. I'm going to minimize this so we can see everything. All right. And I hope that you guys can still see this. If you cannot, let me know and I'll see what I can do to make it more visible. Hey, Keeper of Maps, welcome to the stream. Lurking. That's right. You're at work right now. Too late. I thought a line was always a single axis. Yeah, it's most convenient whenever you make that line to be along the axis. But if that line's in 3 dimensions, then oh man. Hey, Binary Ablaze, welcome to the stream. Yeah, we're picking up where we left off in last week's stream. And so I've already made a few corrections to the calculations that I was showing last week. And those corrections primarily were aimed at how I was treating the rest masses on the right-hand side of the equations that I'm showing here. And so I'm gonna go ahead and still make the same modifications to this too. First modification. Let's get rid of subtracting off these rest masses first, because they're not needed. They're incorrectly placed there. So that's first. Now I considered doing this offline, but then again, if I did it offline, you guys wouldn't know exactly what modifications I made. And the next step, of course, is to then go ahead and square each of the rest masses inside of the square roots, because they should be squared to make it dimensionally correct. I remember when I first started doing problems like this, all this stuff was so confusing. Alright, so now that that's been corrected, moving from the top equation line to the second equation line that's currently being shown on the screen, again, I need to get rid of the subtracting the rest mass in that first term on the right-hand side of the equation. In fact, that has to actually leave in all the others as well. Just quickly do that. Okay. All right. So I think we're good now. Sorry if I got really loud there. But we're good now. I think everything's been corrected. So let's make sure that you guys can see what I'm seeing. Perfect. And so now what's happening as I move from the first equation line to the second equation line being currently shown within the PDF document, I'm considering the fact that the mass of neutrinos is really, really small. And because of that fact, the rest mass energy term relative to the, I'll put quote unquote, kinetic energy term, which we kind of see in the momentum times the speed of light, that quantity squared. So that's like almost like the kinetic energy squared. I mean, almost, not exactly. But as we can kind of see, those two terms, the rest mass energy term will be really, really small compared to that. It'd be negligible. So we can actually set that term equal to 0. And the equation can be reduced through the following 4 equations that we see on this screen. And so the key thing that I want to note is as we transition from the 4th equation line to the 5th equation line, we're able to do so due to the arguments that we were able to generate through conservation momentum. That is, the sum of the magnitudes of the momenta for each of the neutrinos is going to be equal to the momentum of the electron. Magnitude speaking. Not so much worrying about the actual vector momentum. And so as we continue from this, which I'm going to go ahead and actually start up a new line. Well, a new I'm going to put it in its own array, latex array. All right. And so as I typeset that, we'll end up getting this, and I might have to correct this as well. Let me make sure. Let's see. This middle term goes away. And the term on the right-hand side will stay the same. There we go. So we end up getting this. All I've done is move the quantity c times the momentum of the electron to the left-hand side of the equation. And now I have to square both sides. So I can just basically copy and paste this and put parentheses around it as though I'm squaring it. And I can get rid of the square root on the right-hand side of the equation. So far, so good. And so we can go ahead and we can expand the quadratic term on the left-hand side of the equation. And what we'll end up getting is something that looks like the following. Typesetting here. All right, so that's good so far. And of course, we'll get 2 times m sub mu times the c cubed, if I'm not mistaken. And this will be times a times the momentum of our electron. And I've done nothing to the right-hand side of the equation, as that can remain the same. And so as we see here, let me go back to comments to make sure I'm not missing anything here in the comments. And also, it looks like there's a lot more people here I need to say hi to. I could be wrong, but I quickly looked at the numbers and I don't want to miss anybody. So Master Chupun, welcome. Terminus, welcome. Or Terminus 1961. And Tom Van Scotter. Everyone, welcome to the stream, guys. Great to have you here. All right. So, make sure I'm also not missing any comments. Oh, I'm sorry. So, Larry of the G Cloud, you asked. Seriously, the axis of what? So earlier when I was talking about the straight line, I was talking about the line that you'd make with the vectors for the 2 neutrinos going in one direction along the line, and the electron vector going in the opposite direction along that line. And it just so happens to be easiest if you make that line along an axis versus making that line in like some 3-dimensional space, because then you have to consider the components in the 3-dimensional space. The momentum components, that is. Excuse me. All right, so what we can do here, guys, is we can actually cancel out some terms and make this so much easier. Note, the way in which we get to the maximum kinetic energy for our electron is through finding the not the potential energy, but the momentum of our electron vector. And as of right now, that is the only unknown in the equation that we have here in front of us. All right, so I'm going to go ahead and cancel out the middle term on the left-hand side of the equation with the first term on the right-hand side of the equation because they're identical. And this really makes solving for our momentum of the electron way easier. wait. I'm going to continue and still make mistakes. I'm seeing now that I forgot to make sure that the rest mass within the square root was squared. So let's quickly do that. I think it's a simple matter of me just copying and pasting. Oh no, I'm running out of time here. I really want to get to the second problem that I have set up for today. All right, that corrects those up there. Let's quickly correct these down here. I love copying and pasting. It just makes things so much easier. All right, that's that. All right. Now, of course, guys, the reason why I'm doing this is to make sure things are dimensionally correct. As of right now, each term should have units of basically energy squared. All right. So now we want to isolate the momentum. And to do that, I'm going to go ahead and just write it out. I'm going to go ahead and just write it out in its full form, which would be c. It's going to be a fraction. It'll be c to the fourth power. Actually, I could just completely write it out. I have it right here in front of me. As I said before, I've done the math for it. So it's going to be c over 2 times the fraction of the rest mass, or not the rest, well, yeah, the rest mass of the muon squared minus the rest mass of the electron squared, all divided by the rest mass of the muon, not squared in this case. All right. So we can now conveniently plug in some values for this, and go ahead and actually solve for the physical magnitude of the momentum. I'm going to go ahead and keep my c as c because it's convenient given the units I'm about to use. So for the rest mass of the muon, it's going to be 105 105.7. Let's put a fraction in here. Is that right? Yeah. MeV, which is mega electron volts, which is a unit of energy, divided by c squared. And I'm going to do the exact same thing. Let's make sure this is actually coming out correctly. All right, good so far. I'm going to do the exact same thing for the rest mass of the electron. But now I have to change the value to being 0.511 MeV divided by c squared. And then, of course, I'm going to go ahead and write out, or substitute the rest mass of the muon for the denominator. All right. And so what we end up getting for this is that the momentum of the electron ends up equaling, and this is going to be rounded, of course. I made some shortcuts actually, because if you compare the the rest mass energy of the muon squared relative to the rest mass energy of the electron squared, it's really clear that the rest mass energy of the muon is much, much, much greater. Almost to the point where the rest mass of the electron squared is and it's going to be squared at that. It's going to be negligible. So what you'd end up getting is that the value of this comes to be roughly about 52.85. And the unit, though, given that it's momentum, is going to be MeV, or MeVs per C. All right. And so now we're at the final step. Thank you guys for hanging in there with me through all of this. So I'll quickly do this. And now, earlier when I was writing out those terms that I had to correct, those were the correct, for lack of better words, those are the correct formatting for being able to show the kinetic energy of a particle. So in this case, I'm going to go ahead and write out the kinetic energy of our electron has to be equal to, and to make this easier, I'm going to scroll up and just grab that very first term I used for the electron. Scroll back down. Go ahead and substitute that in, and then subtract from that, because this is the total energy. So to get the kinetic energy, all I have to do is subtract away the rest mass energy of the electron, which is right here. All right. And I can even get rid of these brackets. They're not going to be needed. Okay. And so we can go ahead and plug values in for this. But you know what? Let's make this actually a little bit easier on ourselves, actually. So when we plug in the... No, let's go ahead and do it fully, actually. I was going to try to do some, we could logically think through this and be and see exactly what the answer should be. Kind of, sort of, but it's even easier if you just see the math. At least this one line I'm going to go ahead and write out. So the momentum... Okay, so I'm going to go ahead and plug in the values for each one of these, and you'll see what I mean by... You'll see exactly what the answer is immediately. So for this first one, we're going to end up basically just getting 52.85 MeV, quantity squared. Right. Plus, and the rest mass energy of the electron. The electron. So I'm going to go ahead and plug that in. Right. Undo that. Copy. That's the thing I'm going to be able to do. And I can actually get rid of the fact that this is a fraction. Let's make sure this is coming out the way I want it to come out. Sorry about that. Let's reformat that so it looks right. What have I done? Okay, I see. There we go. This should look better. Okay, perfect, perfect, perfect. I'm trying to quickly run through this. And then of course the very last thing. Right. Should be this. Okay. That is correct. And so, to make a very long story short though, if you look at the terms underneath the square root, the 52.85 MeV squared relative to the 0.511 MeV squared, it should be clear like that the left hand term underneath the square root, that is the 52.85 MeV squared term, is going to dominate the square root. So you actually end up reducing that, and you basically just get the exact same thing, but you could ignore the energy component that comes from the electron. All right. In this next line, we can go ahead and we can see that we can get rid of the square root and the square. So in particle physics, well, in astronomy at the very least, doing stuff like this is kind of what you. I mean, well, you could do it in particle physics too, but we tend to make a lot of cuts in our calculations. That is, if we see one thing is basically really, really big compared to something else, we'll go ahead and cut it out. But in particle physics, I don't know if it's so okay to do that. As many of their values they calculate have many decimal places. And lastly, when you compare these two terms, again, the 52.85 MeV is dominating the 0.511 MeV. And our final answer for our kinetic energy comes out to be equal to, of course, 52.85 MeV, or roughly, so I'll go ahead and put approximately 53 MeV, which is the correct answer. And that was a lot. All right, I have 20 minutes, guys. So I'm going to go ahead, well, 20-ish minutes. I'm going to go ahead and move into the next problem. But this is the correct answer. You can always go online and see if you can verify it by looking up max kinetic energy for the electron in the muon decay. All right. Let me catch up with the comments here. Why not approximately 52 MeV? I think we'd have to round up with this. The 52.85 MeV would round up to 53 MeV if you're rounding to the nearest one. Let's see. Okay, so I think Peter was talking about what I just said. Not bad. Hopefully, everyone, it was clear what I said here. The approximation in the square root reduced the result. Whoa, wait a second. Let's look at that. Oh, but it's not 0.5. It's 0.5 squared. And it's not 52. It's 52.85 squared. So when you look at them, the 0.5 becomes like a 0.25. I see what you're saying now. But yeah, that with the squares on them, it slightly modifies that. I hope what I said was clear though. So if I were to actually work out the physical numbers, but yeah, actually I won't work out the physical numbers, so I want to move on to the next problem. But if you were to square them, whenever you have a fraction and you square it, it just makes it smaller. But do not worry, I will post my PDF to the Weekly Space Hangout Cruise Slack. Yes, I'm so sorry for that. And also welcome. You're a new person here. The safe disaster. The problem is it's above. Let's see. The problem is to calculate the maximum kinetic energy of the electron in the decay reaction for the muon. All right, let me quickly move to the next problem now, guys. So I already have it up. I'm going to go ahead and switch scenes. All right. So today my plan is to move on to talking about, well, going from the very small to the very large. So we're going to go ahead and do an astrophysics question talking about stellar sizes. So let me minimize some of the stuff I already had up. Well, it's okay. I don't have to minimize it. I can leave it up. I'm switching notes now. All right. So the problem. So basically, we have that two stars, or stars located in a certain cluster, where a cluster is basically a region of space that has many, many stars that are more gravitationally bound to one another than your general star population in a galaxy. So stellar clusters are within galaxies. So in this case, we have stars located within a certain star cluster. And basically, you could assume, though, for the stars within the cluster, they're all at roughly the same distance relative to us. So the case we have here is that we have two such stars have spectra that peak at lambda 1, or a wavelength of 500 nanometers, and a wavelength of 700 nanometers. And the ratio of their apparent brightness is the following ratio we see here, equal to 0.091. So our objective is to estimate their relative sizes. Oh, that's cool. So red and blue stars, that sounds about right, if I'm remembering the visible spectrum correctly. um, yeah, so the 500 nanometers would be the more bluer star than the 700 nanometer star. So let's go ahead and jump into this problem. So the thing about stars, or the thing about this particular problem, is that we can use a very useful equation that's been determined and it's been around for quite some time now. And it's basically the Stefan-Boltzmann equation. So let me quickly write this out. And so Stefan-Boltzmann's law states, and I'm gonna put I'm gonna put it in terms of stellar talk or astrophysics talk. So line star. I might have to actually complete this particular problem for our next stream. So what we end up getting is that the luminosity, and really the actual equation says the power output, but the luminosity, because that's what stars do, or that's what stars have. They have luminosity, which is their power output. The luminosity of a star is equal to 4 pi r squared, where r corresponds to the radius of the star. That's the area, times sigma. Sigma is a constant within this equation, times t to the 4th power. Oh, okay. I left something out. I know what it is. Sorry, guys. Give me a second to quickly include this latex package. I think it's AMS Math. And that should correct things for us. And I'm going to try my best to spell out his name. Hopefully I don't get this right. Hopefully I get this right and I don't get it wrong. Stefan Boltzmann? Law. Okay. And so this is the law we're going to end up using to solve our problem today. So as we continue, we can now go ahead and start try to use the information that we have within the problem to be able to apply Stefan Boltzmann's law to be able to determine the relative sizes of these particular stars. So the way in which we're going to end up using this equation is that we're going to divide it by itself. And what I mean by that is the following. Whenever you're making comparisons between two things, a useful way of making the comparison is either by seeing the difference, that is subtracting the two things, or taking a ratio. And what we're going to do is we're going to do a ratio. And so I'm just basically going to take the equation, I'm going to divide it by itself, but I'm going to put subscripts, where 1 corresponds to the first star and 2 would correspond to the second star. And you can literally do this with any equation. You can do this for if you're trying to compare two different objects or the same object that goes from one state to another. Okay, what is it not happy about? Oh, those, okay. Let's do this. Maybe it'll be okay with this. All right. So no indent. Comparing the two stars yields the following. All right, so upon dividing the equation by itself, we end up getting, finally, a fraction of L1 over L2 and this can equal the ratio of their radii, R1 over R2. This quantity will be squared. And I'm just going to repeat this now for the luminosities, or the temperatures, excuse me. T1 over T2. Instead, though, their quantities will be to the 4th power. Let's see what that looks like. Let's see if I can also get things to line up a little bit better here. Let's put an and right there and see what that does for me. That's a little bit better. Sorry guys, I'm doing a little bit of I'm reformatting some things so it looks a little bit better. So for any of you guys who are actually interested in using LaTeX, by all means, you're free to look at what I'm doing in the window at the bottom. So this is the equation that we need to use to be able to find out their relative sizes, where the information that's most important, of course, is the ratio between R1 and R2. So we can resolve this problem for that, and we get the following final equation. And equals, and I'm going to copy and paste that. I'm going to go ahead and put, sorry guys, L1 over L2, that's going to stay the same. And the temperature terms, or the temperature ratio, the T1 and the T2 will end up being, I'll take the reciprocal of that. Guys, also make sure you're checking my math here, because at times I do get things wrong. So the luminosity shouldn't be squared. It'll finally be to the 1/2 power. So 1 over 2. I can get rid of the fact that I'm squaring my the radii, and now this will be t to the 2nd power. So I think this will end up becoming the correct form for the ratio between their sizes. Let me make sure I'm looking at the comments. Thanks, guys. So the safe disaster asks, relative apparent brightness is equal to relative luminosity. So to actually answer that question, the brightness of the object, or another way of putting it is the flux of an object, is actually, and actually we're looking at the equation that better explains what I'm going to say here. The brightness of an object, or its flux, is equal to the intrinsic luminosity of the object divided by the surface area that's being covered by the radiation from that object. So they're not exactly equal. So actually, let me see if I can. I'm running out of time here anyway, so I'm going to complete this particular problem for the next stream, and I'm going to go ahead and answer the safe disasters question. So let's go ahead and pull up OBS software. Let's duplicate scene 3. And so I'm going to go ahead, and you're going to now see some blacks, some void in my screen here. I know it's just me. Don't worry, I'm going to bring up something in just a second so I can quickly answer that question. So Safari, OBS software. Let's add a window. Internet. Google. There we go. And so the appropriate equation to answer your question and I will end up ending with this, is we're going to go ahead and type in flux. Flux equation is what I want. Not that flux equation. Radiation flux. It's an inverse square law. Here we go. So I'm going to try to zoom in on this. Hopefully you guys can see what I'm seeing here. And so to answer your question, in this case, that phi on the left-hand side of the equation, which is the flux, is the same thing as our brightness in this case. And basically what we want to say is the brightness is proportional to the luminosity. But more specifically, that brightness is equal to the luminosity divided by, if you have a spherical object, 4 pi r squared. If the light coming from if the intrinsic light or the luminosity, the power output from some source leaves the source in a spherical manner, this will be the flux from that object, or this would be the apparent brightness from the object at a distance r away. So I hope that answers your question. It's now 1:01 p.m. and so I'm going to go ahead and, as many of you guys have probably already done, grab something to eat. So luminosity is equal to intrinsic brightness times the surface area. Yes, in this case, yes. And so, yes, you ate earlier. I really want to eat right now. I hope you guys didn't hear it a few times. My stomach was kind of growling there. It loves science. My stomach loves science, but it also loves to digest, food at times as well. So, yeah, guys, thanks for dropping by. Again, we'll pick this up during the next stream, and I'll have another problem, a far more complicated problem than these. But yeah, guys, thanks for joining. Until next time, have fun, stay safe. All right, guys, bye.